Hey everyone, thanks for listening. This morning we're talking about reactivity and trends in the periodic table, in particular electrons and how they affect those things. So let's get started. What are electrons? Hey, here's the definition from the book. You also have this in your notebook. If you don't, please copy it down into your glossary. Let's unpack this definition, talk about each part of the definition so we make sure we understand it. Subatomic particle, and the definition means just that these are pieces of atoms. They aren't bigger than the atom. They aren't separate from the atom. They make up the atom. Outside the nucleus means that electrons here, they go around the nucleus, and they aren't in the nucleus itself. So here's an electron, and here's an electron. And these light blue lines seem to indicate, or are meaning to indicate, the electron is flying around the nucleus like this in these paths. We sometimes call this mass of electrons around the nucleus an electron cloud, because they really do. They don't stay in that one little path right there. They kind of go in different paths, but still outside the nucleus. Charge of -1 in the definition. Here's what that means. Here's what we're talking about. You've got a negative charge on an electron means it repels. That means it pushes away from other objects with negative charges. Or if something is a positive charge, like a proton, it attracts. So that's what charge means. And then when we say the mass of an electron is really small, or when it's 9.109 times 10 to the minus 28 grams, we mean that it would take almost 2,000 of electrons, 2,000 electrons, to equal the mass of one proton. So there really is a big mass difference between protons and electrons. And we don't say it here, but protons and neutrons are about the same mass. So electrons are also much smaller than neutrons. All right, so that's the definition. What do you need to remember about electrons? So let's just put this out there and make sure we've got it, all right? So first of all, electrons are part of an atom. Next, they're not in the nucleus. They're outside the nucleus. They're flying around out here. If this is the nucleus right here, and this is the nucleus right here, they're flying around outside the nucleus. Then, you need to know electrons have a negative charge. Protons have a positive charge. Electrons have a negative charge. And then, you need to remember that electrons are really small, tiny, and so their mass is kind of negligible relative to the mass of the whole atom. So, here's a quick quiz. Are you ready? You might want to stop after the questions, think about it if you need to. True or false? Electrons are bigger than atoms. False. Electrons are the smallest particles in atoms. True or false? The nucleus is made up of protons, neutrons, and electrons. False again. The nucleus is only made up of protons and neutrons. Electrons are outside the nucleus. Next question. True or false? Electrons do not attract other electrons. True. Electrons all have a negative charge, so they repel each other. Repel means to push away from. True or false? Last question. Electrons make up only a small part of the total mass of an atom. True. Most of the mass of an atom is made up of protons and neutrons. So we basically ignore electrons when we compute the mass of an atom. We saw this last week, I think, when we were talking about the atomic mass is the sum of protons and neutrons for an atom. Okay? So here we go. Electrons and reactivity. Helium, neon, argon. Oh, what are those? Okay. Reactivity is an element's tendency or an atom's tendency to be part of a chemical reaction. Remember some of the effects of a chemical reaction: heat, color change, light, precipitation, temperature. We said heat. All right. Electrons are key to understanding reactivity, and especially its valence electrons. So I'm looking up at the wall here. You've got this in your glossary, valence electrons. These are the outermost electrons in an atom, and these are the only ones that are involved in a reaction. So once you understand valence electrons and how many there are on an atom, you're on your way to understanding reactivity and how electrons affect reactivity. So congratulations. Press on. A key to electrons and reactivity is the number 8. So very subtle here on the slide, trying to remind you of that. And then in particular, we start with the noble gases. Group 18, far right at the periodic table. We especially want to say that they do not react with anything. And so why is that? What's up with that? And notice here, when I look at them, there's some trend going on here. Neon, argon, krypton, xenon, radon. You should see something very similar about those, especially when you count up the number of dots around each one. So let's talk about that. 8 is great. All right, when it comes to noble gases in group 18, 8 valence electrons means this atom, this element is not reactive. There's no reactivity going on there. Why is that? And also, in the case of helium, if 8 is great, 2 is 2. 2 is great as well. In other words, you can think of an atom as trying to fill its valence electron. We call this place where the electrons are a shell, an electron shell. So anyway, the noble gases don't need, we'll talk more about shells later, but noble gases don't need to give any electrons away to get to 8. They're satisfied, so they don't need to give away any. They have 8 already. Each of these here, atoms, elements, has 8 electrons already. They're fine. Also, they don't need to get any electrons to get to 8. They're satisfied. They don't react. They've got 8. They don't need to give any, and they don't need to take any from anyone. That's why they're inert. Another word for this, noble gases do not react. Here's one way we picture it. You put 8 dots around the symbol for a noble gas. 2 top, 2 bottom, 2 left, 2 right. That means if you use 1 dot for each electron, there's no gaps. Noble gases are full up. They don't need to give. They don't need to give any electrons. They don't need to take any electrons. All right. So let's talk about some other groups. We're going to look at all the groups in the table from 18 all the way to 1, except for the transition metals. We're going to skip those. And I want to look at how many valence electrons a group has. Remember, a group has the same number of valence electrons. And how many electrons that group needs, any element in that group needs to give or take to get to 8, and what that all means for reactivity. So ready to go? Here we go. Oh, and then we'll give an example at the end. We'll give a couple of examples of a reaction. You may have seen this reaction, or you might be familiar with this reaction, but that's what we're talking about. All right. Here's a halogen wrap. Group 17 is what I'm talking about. Outer electrons less than 8. 7 is heaven for halogen. 7 wants to be 8. Seventeen is a group. Take away 10, and you've got 7. 7 is heaven for a halogen, but 7 wants to be 8. 7 wants to be great, wants to be done in a reaction. Halogen will take that 1 off of your plate to make 8. be great. 7 is heaven for halogen, but 7 wants to be 8. Okay, that was the halogens. The oxygen group, we're moving from left to right on the periodic table. In group 16, the oxygen group. Elements in this group: oxygen, sulfur, selenium, tellurium, polonium. That's what we're talking about. Hey, and take a quick look. How many dots are on each of these? First of all, you should notice that there's the same number of dots on each one. The next thing you should notice is that there's 6. That means the elements in this group have 6 valence electrons. So in order to remember that, take the group number and look at the last number in the group number. So check this out right here. I'm going to circle it. 6, 6, 6. Elements in this group will take 2 electrons. Remember, they want to be 8. They want to be great. They'll take 2 electrons. They will take 2. They will not give up 6. So they have 6. They want to be 8. They need 2. Moving on. Nitrogen group. Group number 15. Check this out. 5. Nitrogen group has 5 valence electrons. Elements in this group: nitrogen, phosphorus, astatine, antimony, and bismuth. They have 5 valence electrons. So take a look at the group number again. Take a look at that last number. That also means that when you draw these dot diagrams for these elements, you put 5 electrons. 1, 2, 3, 4, 5. 5 dots. 5 valence electrons. That means elements in this group will take 3 electrons. We're still taking electrons. It's still going to be more efficient to take 3 to make 8 than to give up 5. So we have 5. We want to have 8. They need 3. All the elements in the nitrogen group want 3 electrons in a reaction. Carbon group. Group 14. Here we'll lay it out here in a hurry. You got 4 valence electrons in group 14. You've got 4 dots around the element, around the atom. We've got carbon, silicon, germanium, tin, and lead. But here's where it gets a little interesting. Because you have 4, you could either give 4 electrons or you could take 4 electrons. These group 14 will do either, right? So remember, you have 4. You want to have 8. You'll either give up 4, so go back to previous noble gas, we'll talk about that in a second, or you take 4 to grab 8. These guys are not as reactive as group 15. Boron, the boron group, group 13. What you've got: boron, aluminum, gallium, indium, and thallium. Elements in this group have 3 valence electrons. So check it out. I'm going to circle the 3 again. They have 3 valence electrons. And in this case, they have 3, but they want to have 8. They could either try to grab for 5, which is hard, or they could just give up 3. So what I'm trying to say here, again, is underneath the valence electrons that we're showing here, there's usually another set. So you either create a new set with the 3 electrons you got, or give up 3 to go back to the set underneath. We'll go over that in a second. Alkaline earth metals, group 2, far left of the periodic table, almost the first group. Here we've got beryllium, magnesium, calcium, strontium, barium, and radium. Elements in this group have 2 valence electrons. So group 2, 2 valence electrons. It's getting easier. 2 dots. Elements in this group, they'll most often give up 2 electrons. They'll give them up. They'll get rid of them. And they want to have 2. Wait, they have 2. They want to have 8. So they'll most often give up those 2. All right, alkali metals, group 1. Elements in this group include hydrogen, lithium, sodium, potassium, rubidium, and cesium. I'm reading from top to bottom. Elements in this group have one valence electron. One. You draw one dot around them for electron dot notation. They'll give up this electron. They have one. They don't want to grab 7 electrons. They'll just give up that one, and they'll do it pretty easily. All right. So those are all the groups. We just went over whether they lose or gain electrons and how many they lose or gain. That it depends on the group number. We'll go over that again, but just a second. Let's talk about sodium chloride. Check out sodium here. Sodium has 11 electrons. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And chlorine has 17 electrons. 2, 4, 5, 10, 14, 17. All right, but look at this. Look at the valence electrons. Common table salt, sodium chloride, is a reaction between sodium, Na, alkali metal, and chlorine, which is a halogen. Alkali metals, which group? When they come together and react, sodium, because it has one valence electron, gives up that one electron. It has one valence electron. We knew this because it's an alkali metal, because it's in group 1. So let's see, group 1. Let's just group 1 equals 1 valence electron. It will give up that 1 and then have 8, and it'll totally be satisfied. So sodium's going to give up 1. Chlorine, on the other hand, has 7 valence electrons. It really, really wants 1. That's because it's in group 17, and all the elements in group 17 take 1 electron to have 8 and be satisfied. So if you take this one over here, put it in chlorine, chlorine is now happy. 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons on the outside. All right, so you're asking me, hey, Mr. Weisenfeld, how can sodium lose 1 electron and still have 8 valence electrons? I don't get it. I don't understand. So check it out. Here's sodium. Here's that 1 valence electron out here that we're talking about, right? But let's look at the table too, because sodium, Na, is just 1 proton and 1 more electron than neon. See that? Because neon is 10. So take a look. Here's neon. Neon has 10 protons, 10 electrons. And neon also has 10 neutrons. And I think sodium has more than that. Sodium has, looks like sodium has maybe 12 neutrons. So it also has a couple of neutrons that are different. Anyway, although sodium, this 1 valence electron right up here, underneath that valence electron. So if you were to take this one off and take a look, you have 8 valence electrons in 2 shells. 3, 5, you've got 2, 4, 6, 8 valence electrons. And that means sodium looks just like neon once it loses an electron. So during reactions, this is a good point here, most atoms are trying to look like the closest noble gas. In other words, some gain or some lose to try and bump up their valence shell electrons to look like a noble gas. So let's talk about this a little bit more. In class, I burned a piece of magnesium like this guy's doing. Looked pretty bright, just like that. And we know there was a reaction going on because there was heat, there was light, there was color. What was going on is we were creating something called magnesium oxide, MgO. And that means that magnesium, since it's an alkali earth metal, was losing 2 electrons. So magnesium was losing 2 electrons, but oxygen in group 16 wants 2 electrons. So this is like a great combination, because magnesium loses those 2, oxygen wants those 2. That's a good sign that a reaction can happen when they're paired up like that, when they lose, when one loses and another one gains exactly what the other wants to lose. So like sodium chloride, sodium lost an electron, chlorine gained an electron. All right. Let's boil this down. Let's put a name on this tendency for something to pull electrons off of other atoms. It's called electronegativity. Yeah, it's a big word, but let's break it down. One way you might remember is anything that's electron pulling is negative becoming, because you pull more electrons than you have protons, you get negative. So electron plus negative, electronegativity. So in the next slide, in just a second, I'm going to show you all the elements in the periodic table, and they're all shaded. And the more red they're shaded, the higher their electronegativity, the more tendency they have to rip electrons off other atoms. Bam! Okay, so right now I'm on fluorine here, and I am noticing that fluorine is very red. In fact, fluorine is the most red. Fluorine has the highest electronegativity. So let me write electronegativity up here. Other things close to fluorine are also very electronegative, like oxygen, like chlorine, like nitrogen, like maybe bromine, like iodine and krypton. But things that are low in electronegativity are yellow. In other words, these guys over here, hey, they are not ripping electrons off other things, and we know why in the next slide. But notice you'd like a little smooth kind of color transition between the two, but it's generally going to be true. There's a little bumps that electronegativity increases as you go this way, and electronegativity increases as you go this way. So as you go up, electronegativity increases. As you go to the right, electronegativity increases. That means elements that are upper right, up or to the right, are more capable, more prone to ripping electrons off other atoms. All right, ionization energy. Ionization energy is the flip side. In other words, how easy is it for you to rip an electron off an atom? So energy is what's required to do that. And so it's kind of like the opposite of electronegativity, right? You have atoms that are really good at pulling electrons off. They tend to not be the same atoms that tend to like electrons get ripped off of them. So, okay, let's take a look. Remember, when I say ion, ionization, it means you're adding or removing an electron. And the energy to do that is upsetting equilibrium or creating a new equilibrium balance for that atom. So here's the chart. First, ionization. So once again, we've got some colors, and there seems to be a bluish color on the upper right, purplish bluish, and then a greenish bluish at the bottom left. So what I've done is I'm highlighting right now cesium. They have kind of a funny spelling, but that's okay. Cesium has a fairly low ionization energy. Look at this, 375. Fluorine, remember our pal fluorine, has a fairly high ionization energy. In other words, it is easier to take an ion from an electron from cesium than it is to take an electron from fluorine. And that is the indication of ionization energy. And again, ionization energy increases as you go up and increases as you go this way on the periodic table. So ionization energy, how much it takes to rip off an electron, also has the same pattern as electronegativity. So that's pretty cool about the periodic table, that remember, we might not have known all this information at the start. Like Mendeleev might not have known this when he made the table, but when he organized a table like this, a lot of these trends fell out. In other words, they were true. So first of all, what do you need to remember? Given an element, you need to tell me how many valence electrons that element has. And remember, it's like the group number. All right, given an element, you need to be able to tell me whether that element loses electrons, one option, or gains electrons when it reacts. So which is it? It'll have a certain tendency. And you need to know where that atom is that is most electronegative, the one that grabs electrons the most. And you need to know which atoms have the lowest ionization energies. These ones want to lose electrons. And all this, these two in particular are part of trends. Identifying trends on the periodic table is part of PS2B, the standard we're talking about right now in our class. So thanks for listening. You're not done. There's a short quiz, 4 questions. 4. Well, I might add more if people find them too easy. But anyway, at least 4 questions. Tiny.cc, 2014-317. That's the date for today put backwards. I'll put a link to this also on the in the folder on the Q drive. Thank you.